All right, so we're going to do a conservation of angular momentum example here. So as Halley's Comet orbits the Sun, its distance from the Sun changes dramatically from 8.8 times 10 to the 10th to 5.2 times 10 to the 12th meters. If the comet's speed at its closest approach is 5.4 times 10 to the 4th, what is the speed when it is farthest from the Sun if angular momentum's conserved? All right, so they threw that if angular momentum's conserved on there, so we're going to look at that too. So when something's at its closest approach to the Sun, we call that its perihelion. Helion referring to the Sun. If it's like something that's going around Earth, this would be like perigee and apogee, G referring to the Earth there. So as Halley's Comet comes around the Sun, it's going very, very fast, and as it goes out, it goes much slower. Think about the idea of angular momentum, that if it has a big I value, meaning it's far out, it's going to have a small omega value. Small I, big omega when we think about that momentum conservation. So they're telling us the momentum of our system is conserved, meaning there's no net external torques. But clearly there's going to be a torque between the Sun and the Halley's Comet in this case. However, we tend to say that the angular momentum of the Sun, well, it's not zero, but they cancel each other out because it's unchanged because of Halley's Comet. And so it's roughly the same, so we just cross them out. And that's why we're able to say that the angular momentum of Halley's Comet at those two places is equivalent. Okay, so let's go ahead and set up the angular momentum for a point mass going through orbit. Now you might think, Halley's Comet, Mr. Foster, is a ball, right? So it's a solid sphere. Why aren't we using that? Because it's not Halley's Comet that's rotating. It's Halley's Comet is going around in a circle. So it itself is a point mass on this larger shape, this ellipse. So how we deal with that is we have a point mass, so our moment of inertia is mr squared. Omega we can substitute as the speed divided by the radius, and this only works at these 2 points, apogee and perigee, because that is where the radius and the speed vector, the velocity, are perpendicular. Anywhere else we're going to have to find the component of that velocity that's perpendicular to the radius. So we have these two terms now defined in terms of mr squared and v over r. We're going to substitute those into our momentum equation. We see one of our r's cancels, and the angular momentum of a point mass with a linear speed is now considered MERV, mass times radius times speed. And so I have MERV equals MERV prime. So the radius and the speed are going to be different. Now we're going to make the assumption here that the comet lost a negligible amount of mass as it came around the Sun. It does lose some, but we're going to say it's negligible. And so now we're going to go ahead and solve for v prime here. So let's go ahead and pull those numbers back up. So we had 8.8 times 10 to the 10th times 5.2 times 10 to the 4th, all divided by that far out radius, which was, oops, this is a 5.4 times 10 to the 4th, and divided by 5.2 times 10 to the 12th to find the speed out there. We can do a little bit of work with these exponents, so 10 to the 12th, so I got 10 to the 10th, I got to get another 2, so 10 squared there, so 8.8 times 540 divided by 5.2 will give you 913 meters per second. So is it still moving fast? Yes, it's moving still pretty fast, but not nearly the 54,000 meters per second it was moving as it cruised through that inner solar system. So it spends very little time here by the Sun, and it spends a lot of time out here at the furthest reaches of its orbit. The next time that Halley's Comet will come back in for us to see is July of 2061. So mark that on your calendar. Okay, and that's our example.